Good morning, Trailblazers. This is Mr. Parrish coming to you live from second period again. Obviously, it's a Monday rather than last week where we had so much fun with this. So Miss Rouse not feeling today. Hopefully she'll feel better tomorrow. So if you have her number, make sure you text her and make sure she feels better. I'm going to give you guys 3 minutes to work on this bell ringer. You have 3 minutes to work on this by yourself. Make sure you draw the graph. And then if you need to look at your notes for the combined gas law, that's where you can find the information and what this graph should look like. You probably recognize this question from the quiz on Friday. You have 3 minutes to write down the graph and to write down the question. You can do it on separate sheets today. I'm just going to take attendance here for second period. Don't mind me. What are we missing today? Casper is here. Jackie. Who else? That's it? Good job, second period. Got about 1 more minute. Oh, you guys always have an excuse for everything, don't you? All right, there it is. Okay, when you are looking at gas law graphs, there are only 2 acceptable graphs. Okay, so if that's one of my x and y, there's either an inverse relationship where it looks something like that, and then there is a direct relationship where it looks like this. Okay, so of the 2 graphs, you should know that this graph law is for Boyle's law. O-Y-L-E. Yes. I could have just abbreviated, I know, but I'm getting better. Okay, this is Boyle's, right? And Boyle's only involves pressure and volume. So the only time you should ever pick the inverse graph is for pressure and volume. All other gas laws are direct relationship. So you have to check the labels here. This is pressure and temperature, so that is not Boyle's law, which means it is not an inverse relationship. It is a direct relationship. So when you have a question like this, it's phrased kind of weirdly, but what you should do is draw the line and make sure it goes through the point A. So in this case, it's a direct relationship. And then it says, if the temperature was decreased, in what region would you predict the next data point to be located? So, here's temperature, right? If temperature's decreasing, it should be moving to the left. So point A would be moving on this line to the left. So what region is that? Region 3, right? So that's how these questions work. So just one more time, draw the line, then read the question carefully. The only acceptable answers are region 2 or region 3. And since it's decreasing, it's region 3. If it was increasing, it would be region 2. These questions are kind of tricky, but if you draw the line, it makes it a lot easier. You first have to know which line to draw. Yes? The graph can never go in gas law, like this? No, it can never do that in a gas law. It's either inverse or it's direct. Okay. Oh, well, that was... Okay, well, now you just see it again. It's a little bit neater, I guess. I like my version better, but whatever. Okay. Take out your packets, please. Turn to page 26. So in about 15 seconds, you should be on page 26. All you need is a calculator and a pencil or pen. Actually, and your periodic table. So I'll give you 30 more seconds. Take out a periodic table with a reference chart. And a calculator. I wonder if I can turn on the videos. All right, so now you should have those things out. We're on page 26. Today we're talking about the ideal gas law, which is just an extension of the other gas laws we learned. The quizzes from Friday were pretty good. The grades should be updated. You should get your free response back tomorrow by the latest. I think most of you guys are getting this pretty well, and the algebra looks really good, which is a good sign going into common assessments. I should add this to the slide actually. We're going to take our gas laws test, so our summative assessment, on Thursday. The reason we're doing it on a Thursday and not a Friday like normal is because we want to use Friday to get started on common assessments. The chemistry common assessment is next Wednesday. We've been doing reviews as bell ringers. You guys are prepared. You have the skills. We just need to go through some stuff that might refresh your memory a little bit on Friday and Monday. And make sure we are very purposeful with our time. As long as you do what we ask you in class on those days, you should be fine. I'm also going to have Saturday tutorials this Saturday from 9 to 12 for anybody that likes to come up here and work on their common assessment review packet, which you should get on Thursday or Friday. Any questions about that? Excellent. Okay, on the ideal gas law, so at the top of page 26, I want you to go ahead and fill this in. All right. What we did was we just labeled things that we already knew. The ideal gas law is different from the other gas laws because there's no before and after. It's more like a gas in a particular instance. So you can see there's no P1, there's no V2, there's no T2, right? If you have one of each and there's no change, you should use the ideal gas law. Because I think sometimes people get so caught up in the combined gas law because they're so comfortable with it, they start trying to use it when they're not supposed to. So if you just have one of each, you should use the ideal gas law in this situation and not the combined gas law. You can see there's this variable R right here that we're not familiar with. It's called the gas constant. There are 3 acceptable gas constants. This one here, which is 0.0821, 8.331, and 62.4. This is a unit. This is not like a equation. You don't plug numbers into this. This is a unit that helps cancels out. In math, constants are used to help cancel out extra units. So basically, that's the simplest way I can put it. Does anybody see the difference between these 3 constants? Like, why are there 3 values instead of just 1 for a constant? Does anybody see the difference in the units? What's the difference? Adrian, what do you see? They get bigger. Yep, that's true. The numbers are different. Look closely at the units. What's the difference? Arturo? Yep. Right. So what Arturo said was there are 3 different units of pressure. Liters is the same, moles is the same, Kelvin's the same on each of them. But if there's 3 different units of pressure, you have to pick which one is appropriate. So if they give you pressure in atmospheres, you would use this constant. If they give it to you in kilopascals, you would use this constant. If they give it to you in millimeters of mercury, you would use 62.4. So that all depends. Now, you are not expected to memorize these 3 constants. They are, if you look on your periodic table reference chart, go ahead. Under constants and conversions, you can see it's right beneath the pressure values they gave you. The 3 constants are always provided for you. So you're not expected to memorize them. All you do is just plug in the number and you're good. All right, let's go ahead and do the sample problem or the example problem. Oh, wait, no. Sorry, one last thing. This is a multiple choice question that sometimes comes up. Ideal gas laws work best at high temperatures and low pressures and with the fewest number of moles. So remember, this is just a model for how gases behave. This is not like the end-all, be-all of everything we know about gases, but it works best at high temperatures and low pressures. I want you to talk with your table. Why does the ideal gas law work best at high temperatures? Think about that. I'll give you 30 seconds. Talk with your table. What do you guys think? What happens when you start to lower the temperature of the gas? Not just a solid. What does it turn into first? Interesting. All right, time's up. Syra, why do you think that things work best at high temperatures? So Syra said the particles are constantly moving. That is true of gases. Well, let me ask you this, guys. If you lower the temperature of a gas, if you start to lower the temperature, what happens to that gas? Alfredo? It gets colder, and when gases get cold, they eventually turn into liquids and solids, right? So, of course, the ideal gas law works best at high temperatures because things are gases at higher temperatures, right? If it was at a lower temperature, it would be a liquid or a solid, and it wouldn't behave like a gas. Okay. Sample problem number 1. So the steps for this are very much similar to the combined gas law that we did last week. So we'll start by labeling what we have. So we have a 5.60 liter sample. That's going to be our V1. It says ideal gas contains 0.954 moles. That's going to be our N1. And they give us the pressure at 742 millimeters of mercury. That's going to be our P1. So we need to calculate the temperature in this case. So when I look at our equation, I have one of each, so I can't use the combined gas law. I must use the ideal gas law. So PV equals nRT. Now they gave me P here. They gave me V here. They gave me N here. I'm looking for T. Where can I find R? Where can I find R? Patrick, where can I find R? Not sure? Jennifer, where do I find R? You're not sure? What does R stand for? Talk with your table. What does R stand for? Okay, it stands for ideal gas constant, meaning it does not change. Things that don't change you can always find on your periodic table. All right, so we'll talk about that more in a second. So let's start plugging in our values. For P, it's 742 millimeters of mercury. For V, it's 5.6 liters. Is equal to the moles, 0.954 moles. Now comes time for R. We have to pick between these three constants. Right? So based on what? How do I figure out which one to use in this case? Jerry, which one am I going to use in this case? Millimeters of mercury. How'd you know that, Jerry? Right. So in the equation right here, they have millimeters of mercury. So I have to find the one that matches that. This is atmospheres. This is kPa. Here's millimeters of mercury. So I'm going to plug in 62.4. And remember, this is a unit. There are no numbers attached to this. This is just the unit for the gas constant. Just leave that alone. Don't plug in more numbers here. All right, and here we have to find our temperature. That's what we're looking for, T. So this is pretty straightforward algebra. We're going to multiply both these numbers on the left side. We're going to multiply both these numbers on the right side. And then we're left with, we got to get T by itself. So I always draw this step out. I always recommend to my students to draw it out as well, because so many students mix up this algebra. 59.53. I'm getting better, guys. And then on this side, 59.53. Yes. Cross that one off. Okay, and my final answer is going to be 69.8 Kelvin. Wow, that's cold. That's like negative 200 degrees Celsius. It's like negative 300 degrees Fahrenheit. That's very, very cold. But that's what we get. So that's our value. If I look at my significant figures, I have 1, 2, 3 here, 1, 2, 3 here, 1, 2, 3 here, and my final answer also has 3, so that's my final answer. All right. Sample problem number 2, I want you to go ahead and label everything that you have. Go ahead and label everything that you have. All right, let's start taking a look at this one. You can see 19.6 grams. That's kind of odd. We don't normally get grams, so that's our mass. So we'll figure that out in a second. 27 degrees Celsius is our temperature. You should always convert temperature to what? Kelvin. So you add 273 to that. And then this is going to be our pressure in atmospheres. So we have temperature, pressure. We're looking for volume. Right? 27 is the number they pick a lot in AP chemistry because you're not allowed to use a periodic table. And so 27 works out great because it gets to exactly to 300. So it helps you do a lot of mental math. This 300 is easier to work with than, I don't know, fun fact. Anyways, PV equals nRT. So we have P, a little check marks here. We're looking for V, so that's going to be our little question mark. N, we don't have either. R, we always have. That's constant. And temperature, we do have. So we have a problem with algebra here. We have two missing variables. Any ideas on what we can do to find moles or volume before we start to plug in? Any ideas? Irving's looking at the wall. That's a good option. Yes, Caitlin, tell us what to do. Use the conversion chart, right? Stoichiometry. We can go from grams to moles. Right? We know how to do that. Stoichiometry coming back again, guys. I'm telling you, it's so useful. It's wonderful. So we're going to use mass to find moles. So we have methane. They tell us it's CH4. So we have 19.6 grams of methane. We're going to multiply by a fraction. Make sure you're writing this down. On the bottom is grams, so I'm going to put, on this, we start with grams, so that goes on the bottom. And I want to get to moles, so it goes on the top. If it's moles over grams, or moles over liters, or moles over particles, what does moles get? 1. And then for methane, I have 1 carbon and 4 hydrogens, and my molar mass is 16.05 for that. 1 carbon is 12, plus 4 ones gives me 16. When I multiply across, I get 1.22 moles of methane. So now I'm going to take this number, and that's going to be my N1, and I'm going to plug that in for N. Oh, that's an arrow. Better look next time. Okay. So let's go ahead and plug in now that we have moles. We have our pressure, which is 1.59 atmospheres. We are looking for volume. That's our X in this situation. We have 1.22 moles of methane. That's our N. Here's our friend R again. How do I figure out which R to use? There's 3 of them. How can I figure that out? Andrea? The units of pressure. So which one am I going to use, Andrea? Am I going to use option 1, option 2, or option 3? The first one, right? Because it's got atmospheres. So if this is atmospheres, you can see the units match. So our R is going to be 0.0821. And where this is our unit, liters times atmospheres over moles degrees Kelvin. And then we're going to have 300 degrees Kelvin as our temperature. And so now from here, it's basic algebra. We're just going to multiply on each side. 1.59 times V gives us 1.59 V. 1.22 times 0.0821 times 300 gives us 30.05. As always, the last step, I'm going to draw that, 1.59. So many of you skip this step and you do it on your calculator and you flip it. And it's always a multiple choice answer because we know students do it, so make sure you do it on paper. And our final answer is 18.9 liters. Okay, so I want you to talk with your table. How do you know when you're supposed to use the ideal gas law versus the combined gas law? Talk with your table. Go ahead. Okay, Carlos, how do you know when to use the ideal gas law versus the combined gas law? Well said. If there's only one of each, that's when you use the ideal gas law. If they say like the pressure is increasing to this or the volume is increasing, that's when you can use the combined gas law. And the second thing you need to know is like how to find the right R value. And I think we've already went over that. Okay, for this third problem, this one's a little bit more tricky because it involves more stoichiometry. So it says a 3-gram sample of potassium chlorate is decomposed to form potassium chloride and oxygen. The oxygen gas is collected at 24 degrees Celsius and 0.948 atmospheres. What volume of oxygen gas will be collected? So this time, we need to find out the mass of oxygen gas that would be produced, and then we can plug it into the ideal gas law. So what I first want you to do, and I'll try to write this down the best I can, right? First, I want you to write, that's a 1, write, that's an R, yeah. I'm getting better, guys. Write reaction. So write the reaction that's described there. Number 2, find I can't type it. Oh, I guess I could, actually. Let me start a new one of these here. I don't know if it's going to go in front of my... Actually, I don't think I can. Okay, find moles of O2. Find moles of O2. So write the reaction described and find moles of O2. That's your first step. I'm going to give you, let's say, 3 minutes for that. This is basic stoichiometry. No gas laws yet. Just do this part first. Write the reaction and find the moles of O2. 3 minutes. Where's your reaction, Jerry? 7 times, that's where it came down. The symbol is +1. And then chlorate is here on the line. Chlorate, ClO3 -1. Good. So when you write those together, that's going to be -1 and 3. This is +1, this is -1. Cancel. Okay. Decompose, that's your error. And you have potassium chloride, so that's K. What's the charge in K? I wrote it down. +1. Just let me look up chloride. The charges. So there's -3. -2. So it's in this group. So the charge is -1. So +1 and -1. Plus oxygen. So anytime oxygen is by itself, it's one of the 7. What does that mean? It's diatomic, right? So this would be I2, Br2, Cl2, F2, O2, N2, H2. So you Alright guys, this is a more difficult question. Oh geez. Okay, yeah, this is a more difficult question. So, to write the reaction, just going to make me label all this stuff. Okay, to write the reaction, we have KClO3. So that's potassium chlorate, gives you potassium chloride and oxygen, O2. Then you'd have to balance it by putting a 2, and a 3. Right, so like writing and balancing reactions is something we consider pretty routine now. So this is something you are expected to know how to do. If you need help writing reactions, you can come to tutorials today at lunch, or Thursday after school, or Wednesday at lunch. Or Saturday. When I come on Saturday, I'll be here. Okay? Then, we can't go straight from grams to liters. I know a lot of people are like, why can't you just go from the grams, now that we have the reaction, to the liters? The reason we can't do this is because this is not at STP. STP is 0 degrees Celsius in 1 atmosphere. So since it's not at STP, you have to use the ideal gas law. So from here, we have 3 grams of KClO3, and we're going to get to moles of oxygen. So I put grams of KClO3 on the top, moles of KClO3 on the bottom, grams on the bottom, moles on the top. 1 over the molar mass of KClO3, which is 122.55. And then that gets you to moles of oxygen here by you going moles over moles. Do not take this last step to go to liters. You cannot do that because you're not at STP. If it said we're at STP, this problem becomes very easy. All you do is add the 22.4 at the end. But you can't do that here because you're not at STP. So we have moles. So now that we have moles, now we can use the combined gas law, the ideal gas law, to solve from here. So we have our pressure, which is 0.948 atmospheres. We are looking for volume of oxygen gas. We have the temperature, which is 297 Kelvin, and now we have the moles. So we have P, we have N, we always have R, and we have T. So we're looking for B. So from here, now what you do is plug in 0.948 atmospheres for pressure. We're looking for volume. Our moles is 0.0367 moles of oxygen. In this case, we have to find the right R. What is our R value in this case? What is our R value in this case? Adrian? What's the unit of pressure, Adrian? The unit. Atmospheres, right? So that means we need to make this one atmospheres as well, right? The unit of pressure is atmospheres, so that means the R value is atmospheres as well. So we go ahead and plug in 0.0821. And there's our temperature, 297. So from here it becomes pretty basic algebra. 0.948 times V, 0.0367 times 0.821 times 297 becomes 0.895. To get V by itself, we divide both sides. Every time. If it's this hard for me on a computer, you better do it on your paper. 0.94. Ah, 8. Yeah. Khan Academy's got nothing on me. Alright. And now we get V by itself, which is 0.944 liters. Okay, second period. Why can't we go straight to liters here? Because we're not at STP. Okay, if it was at STP, then yes, you could go straight to liters. You could just use 22.4. But here we have to find moles, which we plug into the ideal gas law. Okay, granted, a more difficult question, but still something you can do, right? You can write reactions, you can balance them, you can do stoichiometry to get to moles. and then you can find a missing variable. Not that difficult when you string those skills together. Okay, for the rest of class, I want you working on page 27, which is your homework for tonight. If this was easy for you, I want you to choose the challenge option on page 31. So I'll write this down on a slide here. Okay, here we go. Rest of class. Come on. Homework on page 27. Challenge option. Like question 3. On page 31. All right. Thank you guys so much for your attention. I hope that you work hard the rest of class. Miss Rao will be back tomorrow if she's feeling up for it. We have only 6 more days of class till the common assessment. If you have any questions, I have tutorials today at lunch, Wednesday at lunch, or Thursday after school. Thank you guys. From everybody here in second period. Woo! See you guys out there. Bye.